Okay, today we're going to do the 15-1 doodle notes on what are waves. Don't draw this, but I just want to give you an idea. The first part that we're going to do is going to be the top half of the page, and then this is going to break into the middle half of the page, and then we're going to have the bottom half of the page. So this part we'll be doing on this screen, this part we'll be doing next, and then this part we'll be doing third. Okay, so I'm going to go ahead and clear my page. Okay, so the top third of the page, we're going to talk about what are waves. And there are actually two types of waves. There are waves that need mediums, and there are waves that don't need mediums. Okay, so we're going to talk about the waves that need mediums first. So first of all, we need to define what is a medium. A medium can be a solid, a liquid, or a gas. I like to remember the letter M to help me remember that it is the material in which a wave moves. Okay, so this is, again, I remember the M. This is the material in which a wave moves, and basically these are the particles. So, for instance, in order to knock on a door, the sound is going to travel through the particles of wood. We call these waves mechanical waves. So these are waves that need a medium. And again, I'm going to underline the M here because that M helps remember that if it's a wave that needs a medium, that's the material in which a wave moves, and a mechanical wave, we call them mechanical waves. So for instance, in order to have a wave in a rope, I have to have the rope. The rope would be the medium. There's actually two types of mechanical waves. So we're going to take this section and we're going to divide it into half. And we're moving now to the center of the page. Before I do that, I want to go ahead and fill out this other side right here. So this will be all part of the top third of the page. Okay, so we're going to talk really briefly about waves that don't need a medium. Okay, so these are waves that don't need a medium, meaning they don't need a material in which to move through. They can just go through empty space. So they do not need particles. And they can travel through empty space. And most of these, or I can't think of any right now that would be compressional or longitudinal waves. So these are going to be transverse style waves. So they're going to have that up and down type of motion. So they're going to be transverse, meaning they're going to have this up and down style. And your example of the electromagnetic spectrum, of the types of waves that don't need particles is going to be an electromagnetic spectrum. we have the electromagnetic spectrum there. So again, just to review, we have waves that need a medium and waves that don't need a medium. Ones that do not need a medium do not need particles to move through. They can travel through empty space. They're going to be in a transverse style where the movement is at a right angle to the actual wave direction. And a good example is the electromagnetic spectrum. So now we're going to go back onto this side, and I'm going to change the screen to go ahead for these two. Okay, so we have two actual styles of waves. We have transverse waves and we have longitudinal waves. So we're going to put the transverse on this side. Okay, and then over on this side we have our longitudinal waves. We also call these compressional waves. Okay, so we have our transverse waves and our longitudinal waves. Now, these two are different because of the way that they move, and that's how we identify them. So I'm just going to draw two boxes, one underneath transverse and one underneath longitudinal. Okay, and a transverse wave is going to go basically like a rope, up and down and up and down and up and down. Okay, now what's going to happen is the vibration is going to move up and down like, in order to make the rope go, I have to move, sorry, my hand was in the way there. Okay. So my movement is going to go up and down, and the wave direction is going to go forward. Now if you could see what happened is I just made a right angle. The movement that causes the wave is going up and down, but the actual wave is moving forward. So that creates a 90-degree angle. I think that it looks like the letter T for transverse, where they're moving at a 90-degree angle to the wave's direction. Okay, so as you can see, I have labeled these. Alright, so we have the wave direction, which is going this way, and this up and down movement is going to be the vibration movement. Okay, now a longitudinal wave is going to be different. A longitudinal wave is going to be more like a sound wave or a slinky, where you've got this movement of particles. Okay, and so the movement, if you're thinking about a slinky, is going to be in this direction, back and forth, and the slinky is moving, or the wave is moving in that direction. So you can see that they're parallel to each other. Okay, here they were at a right angle. This was going up and down and this was going forward. But here I'm going back and forth and this is going forward, so that they're parallel to each other. So I'm going to label that part. And so you can see the vibration and movement and the wave direction. Good examples of a transverse wave are a rope or a snake. These all need mediums in which to travel through. So the wave has to travel through the snake's body. The rope acts as the medium for the energy to pass through. So this is examples of snake or a slinky. I'm sorry, not a slinky. A snake or a rope, like a jump rope. Okay, examples of longitudinal waves are going to be slinky and a sound wave. So sound waves will always travel sound waves will always travel, like when you see a speaker, you know, if you're looking at a speaker, the speaker is going back and forth and the sound is traveling out away. So think about a speaker, it's going back and forth. The woofers and the tweeters are thumping, they're going back and forth, and they're creating these circular sound waves that come out of the speaker. Now, you can combine these two together and you can make surface waves, and that's going to be the bottom third of your page. I do want to add to the other page and to the electromagnetic spectrum underneath, I just want you to list the parts of the electromagnetic spectrum. And you have the radio waves. Let's see if I can. You have the microwaves. These are from the largest wavelength to the smallest. Infrared, visible light, ultraviolet, X-rays, and gamma rays. And these are all, oh, something happened, sorry. I need to make my, okay, so those are all parts of the electromagnetic spectrum, and they do not need particles to move through. They can all travel through empty space. Okay, so you can see I got a little creative with my emoticons there. Okay, so now we're just going to do this very bottom 1/3 of the page right here, and we're going to tag on what happens if you take a transverse wave and a longitudinal wave and you kind of put them together. What kind of wave are you going to get? And we call that a surface wave. A surface wave is a combination of a transverse wave and a longitudinal wave. So not only is the object going up and down and up and down and up and down and up and down and up and down, but you also have these little circles going on as well. And our best example of this is an ocean wave. Okay, and that's all we have for our 15-1 doodle notes.